recording now. And we have asynchronized counter versus synchronized counter, right? There is another name for the asynchronized counter, which is basically called rebel counter. Rebel counter. So if somebody told you that, I want to build a rebel counter, basically it's talking about what? Asynchronized counter. Sounds good? I told you that, when the circuit is synchronized, what will happen? It means that, if I have a 3-bit counter like this, and this is a 3 bits, that means 3 flip-flops, then, all of them are sharing the same what?
Clock.
Clock, exactly. This is synchronized. The asynchronous, that means, every single one has its own clock. But normally in the rebel counter, what happens? One passes to the other. What does it mean? So in the rebel, if I have a 3-bit like this, right? Then, I have here what? My clock. Then my Q here will be the new clock for the second one. Then, the output here, it will be the clock for the third one, and you move forward. This is one of the form of the asynchronous counter, and we call this what? Rebel counter. Of course, you're gonna extend wires here to get the outputs and stuff like that. You know what I mean?
How about if the Q does not change?
How about what?
How about if the Q does not change? So it's the input of the Q of the first one does not change. So the output.
You mean this one, keep it with 1 and stuff like that?
Yeah, if you keep it at 1.
Oh yeah. That's something really famous. Yeah. Because that's actually, do you remember JK flip-flop? And the JK flip-flop, right? If I'm gonna use it like this, you're gonna do it like this, right? JK, right? JK, right?
Mm-hmm.
Key is the clock. Key is the clock. Key is the clock. Then you will come here and say that I want this to be trimmed like this and connected to 1.
And that'll be a D flip-flop.
They're gonna be exactly T flip-flop.
But then didn't you say that the output of the Q is connected to the clock of the next flip-flop?
No, I'm talking about this synchronous. Yeah. They're gonna go here. So you remove this. They're gonna go here. They're gonna move like this. And then you get the output from the Q itself. That's a rebel counter. That's not synchronized.
Mm-hmm.
You understand the trick, right? I will show you what is the trick. Do you remember when we count? Let's say that's 3-bit I'm counting, right? 0, 1, 0, 1, 0, 1, right? 0, 0, 1, 1, 0, 0, 1, 1, and then 0, 1. And then here 1, 2, 3, 4, 1, 2, 3, 4, right? This 1 and 0 are actually drawing what? Clock, right? Do you agree? Look at the waveform, right? Let's say this is Q0, this is Q1, this is Q2. Sounds good? Now, Q0, 0, sorry. Right? And then here 2 zeros. So and then here 4, right? So at the end of the day, what you are doing, you are shaping what? Different clocks, right? That's why you are using the output of the first one to be the clock for the second one and so on. So the trick is basically what? If the first flip-flop using clock, right? The second flip-flop will be using clock divided by 2. The third flip-flop will be using clock divided by 4. The fourth clock gonna be clock divided by what? 8. And you continue. Huh?
Yeah, makes sense.
You understand my point? Because, you know, if you think about it, look what's actually, you know, let's say that, you know, okay, let's say that, you know, I have 4 flip-flops, right? 4 flip-flops, right? Sounds good? Then, you know, the first flip-flop, its own clock. That means this is my external source of the clock, right? Then, you know, that first one is bringing me the Q0, right? Basically the output, right? That output is what? It will be F1, F0, right? So my F0 is basically clock. Now I'm taking the F0 to be the clock for the second one, right? To the flip-flop number 1. This is 0. Let me just allow a bit more. So now we're gonna work like this, you know. I have F1 is equal to F0 divided by 2. Right? Which is basically what? F0 is clock, so gonna be clock divided by 2. Now I have flip-flop number 2. F2 is actually F1 divided by 2, which is what? It's gonna be F0 divided by 2 divided by 2, which is basically what? F0 divided by 4, which is basically clock divided by 4. Now I have flip-flop 3, which is F3, which is equal to F2 divided by 2, which is basically F1 divided by 4, which is basically, you know, gonna be F0 divided by 2 divided by 4, which is gonna be F0 divided by 8, and you continue. Now you understand what I'm saying? Hello?
Yep, makes sense.
That's why I didn't want to put too much on it, because, you know, it's still counting, right? You just need to know the difference, right? The only difference, you know, the synchronized, all of them sharing the same clock, right? For the asynchronous, every single output is a clock for the consecutive following flip-flop, and then you will move forward. And what you are doing, you are fracturing by the 2. And, you know, if you look at it, it's accumulated. So it's gonna be 2 power 1, 2 power 2, 2 power 3, 2 power 4, and so on. Okay, look. Anyway, one of the design problems that we ever can see, we already talked about up counter, right? And we talked about up counter with reset, up counter with enable, and we have seen how that will be reflected on the graphical representation of the finite state machine, followed by the state table. And then, you know, I asked you for, like, you know, self homework for filling the tables for the, I think, reset, right? And then, you know, I gave you the enable, and I told you go and make the implementation. Do you guys remember that?
Yes.
Okay. If you already have done that, that will make it easy for you for the rest of this course. It's because the whole course is a piece of cake. Anyway, now, what about if I would like to do a down counter? I'm doing what? Down count. I'm gonna still use the same what? Same trick. Do you guys agree? So imagine that, you know, I would like to implement, you know what, let's make it easy. 2-bit down counter. 2-bit synchronized down counter. And this counter, once you connect the crystal, it will be working. That means we don't have what? We don't have like a control enable or whatever, right? What exactly the way that you have to approach this problem is basically to build the state table, right? So, you know, my state table like this. I have here what? 2-bit, so that means gonna be QA, QB. And then I have here QA plus, QB plus. I know since I said 2-bit, that means 2 flip-flops, right? So how many states this table will be covering?
4.
4. 1, 2, 3, 4. 0, 1, 0, 1, 0, 0, 1, 1, right? Now, it's a decrementer. It's a down counter. So what does down counter mean?
You start from the highest
4, 3,
MSB.
2, 1.
I mean 0. So what is the next?
4.
4
4, not 4,
or 5. Sorry.
not even 5, 3.
Three.
3. Sorry, yeah, 3.
2, 1.
3, 2, 1.
Okay, 1, 1. Anyway, I'm in 1. What is my next? 0.
1, 0.
0.
What?
Yeah, you have
Oh yeah.
decremented.
Oh yeah. Oh yeah.
Oh, pew, pew. You know,
Wait,
come on,
no,
you know.
you're decrementing, right?
Yes, so I'm in 1, I'm decrementing, so I turn it back to 0, right?
Yeah.
I'm in 2, decrementing, it will be 1.
1.
Yeah.
Yeah, I'm in
3.
decrementing, so it will be 2.
Oh yeah.
Oh, come on.
Oh man.
C plus C, you know, C in T is equal 3. C in T is equal 3 minus 1. C in T minus 1. Right? Have you guys
Well,
used
I thought if you're decrementing, isn't it 3, 2, 1?
why? You know, wait.
But
I'm
you
starting
are,
from
though.
3. So I'm gonna go 3, 2, 1, 0 back to 3. So I'm decrementing. But while I'm decrementing, there is corner case. By the way, later on, you guys, when you go to the higher level courses, you're gonna hear something about verification and testing. And in this, you know, you have to look to corner cases. But you know, don't worry about corner cases now. We are caring now about, you know, if I have a ring, the counter is a ring, right? So there is edges. When I reach one of the edge, for sure I will go back to the edge, the other edge, right? You remember Alaska and United States? K-map, same thing.
But isn't this incrementing then? It's from like 3,
Why I'm
1,
incrementing,
0,
I'm
1,
decrementing.
2.
Because, you know, I'm in 0, right? I should go back to what? When I was up counter, I went to 1, right?
You have to make the model. I don't think he'd understand if you don't make the model.
Like the present state is counting up because
It's like
that's how you
modular.
have to run through.
Mm,
But then the next state is what's decrementing from the present.
exactly.
I think he just confused because we don't start at 4 because we don't have 1, 1. It'd be
Yeah.
There is no 4, right?
Mm-hmm.
correct.
It's a 2-bit.
Okay.
So
Yeah,
a
yeah,
2-bit
okay.
maximum will hold what? 3.
Up to 3.
3.
Maximum 3.
But I think he assumed we start at like our first input was 1, 1, and then it goes down. You know what I'm saying? Like it's reversed instead of 0, 0.
No. Because, you know, in up counter, if I'm in 0, where I'm gonna go?
1.
To 1. Ha! Now, because I am down counter, I start from 3, right? If I am 3,
Yeah.
I go where? 2.
Yeah.
Here.
Yeah.
But because of the order, you got confused.
Yeah.
Make sense?
Gotcha. Okay.
Okay, $5, please. Okay, anyway, so now we finished the most important part, which is basically the building the state table. Anything else, a piece of cake, right? Because I have 2 flip-flops that mean translated to how many states? 4 states, right? Either that I like to write it 0, 0, or whatever I want. I can do it like this, right? So I will just do it here 0, 0, you know, 0, 1, 1, 0, you know, 1, 1. If I would like to name it, that's fine. You know, I can just say that S0 is 0, 0, S1 is 0, 1, S2 is basically 1, 0, S3 is basically 1, 1. And I gotta look more fun, you know. Anyway, so now I'm in 0, I will go to 3, right? I'm in 0, I will go to 3. I'm in 3, I will go to 2. I'm in 2, I will go to 1. I'm in 1, I will go 0. Very naive, simple state machine, right? If I would like to finish my design, I have to nominate a flip-flop to be the one I'm gonna use for implementation. Say, extend my table here. And basically, because if nobody told me that, you know, which flip-flop I'm gonna use, so I will just use what? I will use the T, right? So I'm gonna have here TA and TB. And as I remember from our discussion, that's an XOR, right? So this is 0, 1, it's gonna be 1. This is 0, 0, they're gonna be 0. This is 1 with 0, they're gonna be 1. This is 1 and 1, it's gonna be 0. This is 0 and 1, it's gonna be 1. This is 1 and 0, gonna be 1. This is 0 and 1, it's gonna be 1. This is 1 and 0, gonna be 1, and we'll be done. Then, you know, you're gonna make our lovely K-map. This one doesn't need a K-map. This one is directly 1, right? While this one, it's an Gonna be this two term, right? This one and this one.
Can you toss a multiplexer in it and just call it good?
It's up to you, you know.
Like a 2x1 multiplexer?
Basically, let's say that I came into you one day and said that, hello, build this circuit using multiplexers and flip-flops. If I just keep it open like that, you can do whatever you want, right? You agree?
Yeah.
Okay, anyway, now at least we understand what is the trick of the down counter. What about if somebody tell you that, you know, I want to reset, I want enable, stuff like that, you will find, right? Something to be tied to your labs, right? Because you guys also take 2300 lab, right? In the lab, sometime, you know, you'll find the IC you get, right? In this IC, if you open the data sheet, it's a TTL, right? Have you guys heard this term, right? TTL?
No, what's a TTL?
TTL. It's technology used for building the flip-flops and the circuit using transistors. It's called TTL. You never heard about it?
Nope, that was the first time.
Haven't come across it.
Interesting. You know, I mean, if I teach a lab, I will do it first day. All of the circuits you are buying from the internet, all of these ICs are TTL technology. Do you know the story? All of this stuff built in front of you are not real. And end of the day, we are using transistors. We are using something called CMOS. You know what this, right? This is a combination between NMOS and PMOS. There is a course, it's an elective course in the 4000 level called VLSI. If you guys will take it in the future, you will see stuff like that. And CMOS is basically combination, it's called complementary metal oxide silicon. So basically, you know, you build it like that. VCC, ground. It is the input, here's the output, and this circuit will be acting as what? Inverter. So this is the NOT gate. In reality, this is the NOT gate on the silicon. So, you know, you have to use some voltage track and current. That's why they call the ICs built TTL. TTL. Let me search for you. I think I know the exact name. It's TTL stands for transistor. Wait, what's after TTL?
Transistor logic.
Yeah, no, I was saying.
So if I were to put those together, like if I were to have two like gates, like the AND gate, right? Would you put those in like together? How do you make an AND gate out of it?
This is transistor logic, yes. Go ahead. Huh? You want AND gate?
Yeah, how do you make an AND gate out of this?
Wait, I'll do it for you. I will do it for you. Okay. No, actually, I made this is NOR gate. I'm sorry. I'll make you AND gate now. Okay. Here's the ground. Here's an A. Here is an B. Here's the VCC, and here's the output. What I did here, this is actually A. This is NOR, right? So NOR is what? A, B complement, right?
Wait, so the A is on that side and the B is on that side? So where's
Because
the output?
wait. If this one went out, this one is producing. If this one went out and this one exists, the other one will pass to the ground. That's why it's what is like OR, but OR inverted. But if you would like to build NOR, that's why, you know, there is nothing called in the circuit NAND and then OR and stuff like that. In the silicon, just NOR and NAND. NOR and NAND, inverter. So NAND here. It's a configuration stuff, you know what I mean? Baby output VCC. This is your 2-input NAND gate. If you want AND, what are you gonna do? You will take this output and you connect it to this inverter, and that will be NAND versus NAND inverter. So it's gonna be AND. That's why do you remember this equivalence stuff I was actually pushing on you to learn? That's actually used for that. Okay.
Yeah.
Makes sense? Have you ever guys heard about transistor? Did you hear about semiconductor? Hello?
Oh, no.
And semiconductor is basically something between conducting and not conducting. You know what I mean? So basically, what they are doing, it's in the MOS technology, you already have here like a substrate, and this is a positive charge. They call it hole or P. And then you already have N. You already have N. And here is basically the injected P in the middle. And then there is here metal oxide metal. And then they get the gate. And here's the source.
This is to act like a resistor, right?
Yes.
Oh.
Transistor. And the transistor has a characteristic curve like this. Then you already have here cut off, that means it's turning off. Here is saturated, that means it's turning on. Here is basically transition. Transition is used for some other stuff. And based on the voltage on the gate and source, this curve can be like this. It's a different course. Don't worry. Okay. If you guys have time, I will give it to you. I will give you another lecture about that. But anyway, back to the point. Design, down counter, the whole trick, decrement. Do you agree? Adding all of this piece stuff, that's fine. When I wanted, actually, my intention when I start talking about this, I wanted to tell you, sometime when you open the manual for the TTL ICs, you will find the flip-flop like this. What is this? We know the flip-flop without these two things, right? The flip-flop, the insert inside the reset. This is a reset. And also there is something that's called preset. What is preset? Preset. So if you push reset, that means I put it 0. If I push preset, that will be making the flip-flop equal 1, the initial state. This is from the circuit perspective. Okay. Hello.
Yep.
Okay. Hopefully, I'm not confusing you. I'm just telling you what is in the data sheet.
So when the preset is 1, does that mean the Q and Q?
It depends on your active high or active no. So
Okay.
what's preset? Preset, it means that, if I click on it, that means the initial of this flip-flop equal 1. That means I set it to be equal 1. You remember set and reset in the latch?
Yes.
Same. But of course,
It's
with respect of the clock. Yes. Go ahead.
No, I think I answered it. So it sets one of them to 0 and the other one to 1, or?
It depends on which one is active low and active high.
Got you. Okay.
Some books, if you would like to do this with active low, right? So you're gonna do like this. That means my reset here is active low. This circle make it active low. Okay, look. Sounds good. Now I want to also to define to you something you're gonna see. It's called synchronized reset versus asynchronized reset. What does it mean? If somebody asks you this question, if you are going for internship, your answer should be very straightforward. If it's synchronized, that means if the reset is high and the edge went positive, for instance, the reset will happen. But if it's asynchronized, it doesn't matter at which location of the clock I'm gonna reset. Again, so let's say scenario for synchronized. Here is my clock, right? Right? And here is my input, which is basically like set of data. Let's say D5, D4, hexadecimal, D3, and I go ahead like this. And now I need to see what will happen if the reset happen here. So here is positive edge, right? And here the reset went high. So I'm actually expecting that D will be turning to be what? 0, 0. That's data bus. Data bus, that means is a set of flip-flops, a set of bits. Okay? So if the edge happen here with the reset at the same time, then the reset will happen. Imagine I'm synchronized, but the reset, for instance, let's make a different, this is reset 1 scenario. Let's make a different color for reset 2 scenario. Like, you know, I have the reset here. Reset 2 scenario. The reset happen here and the positive edge here, right? But the reset happen here. What will happen? Somebody can tell me.
Nothing.
Nothing, exactly, because it's synchronized. You know, both of them, they have to catch each other at the same time. So that means, you know, when it will be resetted, next cycle, if that guy will be high forever.
Oh, so if it doesn't hold that reset information in the buffer.
Yes, this look here, this is high and this is high already. So that guy will reset here. The time it will the reset is high and met the positive edge, data will be reset. That's called synchronized. Now for the asynchronous. So, you know, let's go for the reset asynchronous. Right? I'm here. I'm low. And then, you know, let's say that, you know, I came here and I went high. What will happen immediately, no matter where exactly I am? You know, I'm here in the middle of low or something, right? What will happen? This bus will be what? 0. Because the priority, the above hand, or the full control give to the reset above the clock. Is there any question regarding this part?
So this is active high?
Yeah. Okay. Don't confuse yourself about active high or low now. The whole idea. If somebody tell you there is synchronized reset, what does it mean?
It only reset at the edges.
It resets when the clock hits, when it's high and the clock is high?
No clock high. It's basically on the edge with the reset is high. When it's asynchronized, what will happen?
It'll reset anytime you press it.
When the reset is active, I'm done. Make sense? It doesn't have any relation with the clock. Okay, now the third or the fourth object we need to talk about today is what? Up-down counter. Up-down counter. So if I ask you design 3-bit up, down, synchronized counter. I cannot go up and down without having an external input or an external signal that will control the movement. Do you guys agree?
Yeah.
If such a kind of question came to you, you have to know that the need for an external input to choose the directivity of counting is raised. I cannot go up and down without control, right? Translate this. So if I want, I have to build a table. Do you agree? That table will look like what? This. QA, QB, QC. And then that's actually what? UD up down signal. And the output is gonna be QA plus, QB plus, QC plus. And we're gonna keep this, of course, when we need the T, whatever, right? This table is covering how many states?
16.
16. So here 1, 2, 3, 4, 5, 6. Scheiße. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Sounds good? 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 0, 0, 1, 1, 0, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Then here 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8. Correct? Our assumptions, because we are designing, if UD is 0, this counter is going to count up, while UD equal 1 count down. Make sense? Now, okay, now we're gonna go in this, right? What I said means this is up, this is. Do you guys agree?
Yep.
Okay, so if you want to do it, so now I'm counting what's up, right? Because I see the 0 here, right? So 0 going to what? 1, 2, 3, 4, 5, 6, 7, 0. Right? Do you agree? Now, 7 in the down is going to be what? 6. It's gonna be here 5. You're gonna be here 4. You're gonna be here what? 3. You're gonna be here what? 2. You're gonna be here 1. You're gonna be here what?
7.
Make sense? I think I made a mistake. We're missing something here, right? No. Yes, I made a mistake.
Should be 0, right?
Yeah.
Yeah, it should be all zeros.
Yeah. I made a mistake. That's why I said I made a mistake. 1. Right? We finished what? We finished the whole entire design, and it's a time for us to do what? TA, TB, TC, and we fill the whole entire thing. We build our circuit, and we'll be done. You can consider this as a what? Self homework. Following. Okay, man. Then using flip-flops and associated okay. Any questions so far? Anything is not clear? Hello?
I just noticed something, Professor.
Tell me.
Will the last one of the T always just be 1?
Maybe. Don't forget, I didn't ask for reset and enable and other stuff, right? That might affect. Right? Now, if everything clear, I will share with you the last part before we close for today, and then we'll continue next time. So it gotta be what? No, two things. I'm sorry. So what is the state representation, graphical representation of this up-down counter will look like?
It's just the 2 combined.
Let's see. So how can we do it? S0, S1, S2, S3, S4, S5, S6, S7, right? Now we're gonna use 2 different colors. We're gonna make it easy, right? So S0 going to S1 if UD equal what? 0.
0.
Right?
Yep.
Now it's gonna be the flipping, right? So this one, when UD is equal what?
1.
Correct?
Nope.
So it's supposed to be very straightforward. But what about if you add a reset and enable? how it gonna work. Gonna be more and more complicated, right? But it
Yeah,
should
you'd
be
have to-
a piece of cake, huh?
You'd have to have it so like it goes back to zero, S0, right? All the time.
Yeah, I mean, if you
So-
reset here, look, if you reset like this, right? If not, we'll
Yeah.
continue. Yeah.
Mhm.
And the enable also will be added. So it's gonna be more input control inputs signals to control the movement from a state to the other, basically. But you know, it should be a straightforward process. Do you guys agree?
Yes.
The last thing I need to talk about today is modulo. In general, modulo is ring, right? And the even number of the coming from the power of the number of bits we have make it easy. But what about if we are looking for number of states less than the numbers, you know, the counters can give us? What does it mean? So let's say that, you know, I have a 3-bit up counter. Okay, but what I want you to build, design and up counter, which is counting up to 5. So this counter is counting up to 5. What does it mean? That means, you know, I know that this counter will count 0, 1, 2, 3, 4, 5, and back to 0, right? We know the regulation. How many bits or how many flip-flop this would be taken? It's gonna be the log 2 of number of states here, 6, right? There is no fraction of flip-flops.
Yeah, okay.
So what you need to do, you have to use what?
The highest.
The higher orders. Exactly. But then, you know, what exactly you're gonna do for 6 and 7?
Set it to 0.
It's not set it to 0. I will show
Set
you.
it to 5.
X.
Yeah, so basically what you need to do, you're gonna go like this, right? And then, you know, if we're gonna make it without any control signals, so basically we're gonna say QA, QB, QC, QA plus QB plus QC plus 1, 2, 3, 4, 5, 6, 7, 8. 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 1, 2, 3, 4, 1, 2, 3, 4, right? So when I go to 0, you know, I start, you know, I go to 1, right? 2, right? 3. No, 3. Right? From 3, I go where? 4. 4 will go where? 5. 5 will go where? 0. I don't care. Make sense? Did you see what I did?
Yeah.
Because I will never see 6 and 7, right? They are not in my consideration. I don't care about them. So some people will put it zeros, some people will put it 1, whatever they want. But end of the day, it's better for me to be tricky and put it to what don't care, so I can I find out best way of what making an optimized implementation using less number of resources on the chip. Do you guys agree? As we already learned
Yes.
about what is don't cares. Yes.
But if there's like noise feedback, then what do those X's do? Do they will it like destroy
Those X's they're meant for something. They're meant for what? They're meant for how to say control process. Like, you know, do you remember when we make the K-map, right? When you have some bunch of X's, what it's gonna make it easy for you, right?
Mhm.
So you think about it in a way that they're gonna make it easy for you. Because, you know, look, from here, there is no way for you to go even 6 or 7, right? You're gonna go back to 0, and then you will just go like this, right? So it's better for you to put it X somehow to figure out a way to use it when you generate TA, TB, TC, whatever. Then, you know, it will be less number of what logic gates used for the implementation.
But what if there is like a somehow it magically does get to like a higher number? What will happen? Will it crash or circuit?
That's a very good trick. So, you know, that's why, you know, I will leave it like this so you guys can think about.
What happens to the excitation table with the X's?
That's also very good questions, you know. Think about it. Do you want it to be 0 or do you want it to be what? So for instance, if you go like this, right? Right? And here is TA, TB, TC, right?
Can you just make them X's then?
So, yeah. So 0,
okay.
I think it will be X, yes. 0, 0. Here is 1, right? Here is 0. Here is 1. If 1 XORed with X, what the output will be?
X?
Exactly. Now, if you're gonna make the K-map, you will figure out you appreciate this. You guys agree? Right? So let's make a K-map for this. Look. QA, QB, QC, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1, 3, 2, 4, 5, 7, 6, right? So that's actually location what? 3, right? And location 5, 6, and 7. What should we do?
2 groups.
Exactly. So now we are appreciating this X or not? That makes sense? Because without this X, you know, the output should be what? It should be QA complement, QB, QC, ORed with QA with QB complement QC. Look at how many gates you have, right?
Yeah, we have 7
1,
gates there.
2, 3,
8,
4,
9
5,
gates.
6, 7, I believe.
With the knots, right?
Yeah. Right? Now let's use this X. Let's see the appreciation now, right? So basically this is gonna be QA. That will be with QC, right? That will be ORed with QB, QC. How many? 1, 2, 3.
You can combine the QCs too and just make 2 gates.
Okay, let's do it. It's gonna be also 3. Let's see, right? So if you make it, it's gonna be QA, ORed with QB, and it was QC. You want it to be like that?
Uh-huh.
Yes. So basically, yes.
Yeah, that'll be 2 gates.
Hey, Prof.
Wow.
Let me call you in 1 minute, okay? No. I will call you in 1 minute, okay? Okay, look. QBQC and then, yeah, you're right. it's gonna be 2, right? So look, you know, we appreciate this or not? We appreciate it. Make sense? I mean, you can be tricky also, right? Here, you know, you can be tricky. You know, you can just come and say that, you know, QC with QA XO'd with QB, right? I mean, it's infinity games. But you guys understand my concept, right?
Mm-hmm.
Okay, so in that case, I can tell you that we almost over with the counters. Maybe half an hour next time, adding more stuff about counters. We'll go to registers and how can you make a sequential circuit that's gonna shift left and right and rotate left and right versus parallel shifting and parallel rotation based on the barrel shifter have been designed in 1991 or 2 by the Princeton research team. Okay. Any question regarding the material of the today lecture? If there is no any questions, don't forget, if you are still interested, to join the competition thing that I was talking to you, to put all of your information on the link that, you know, one of your, I think Kushal made the link, which is really appreciated. And I will look at it and I will let you know what's going on. Okay. It was my pleasure to talk to you. And I hope that you guys will enjoy the rest of the day and also have a wonderful weekend.
Have a good one, Professor.
God
Thank
bless
you,
you guys.
Professor.
Thank you. Bye-bye. Stay
Thank you,
safe.
Professor.
Thank you.